So let's move on and talk about the quicksort. So for the quicksort, and here are some high-level information I want you to know. So number one, it is a sort-in-place algorithm. So that's cool, right? And then, well, its running time is O n log n in the average case, and it sorts in O n squared in the worst case. Well, however, well, with some smart implementation, and we can really minimize the case of the chances of having the worst case. So usually we consider the quicksort to be another O n log n sorting algorithm. And well, as I said in the earlier video, and I say usually quicksort is a winner among all the O n log n sorting algorithms. And well, the question is, why do we want to use the quicksort instead of the merge sort? Well, the merge sort, remember, the big problem is it will require additional memory space, right? Okay, so for the quicksort, and the implementation is, or the design is very smart, and the idea is we want to do a partition, and for a partition, it means that we want to divide the list to be sorted into two parts. Well, when I'm saying those two parts, well, the size may not really be equal to each other, but it doesn't matter. But we want to divide that into two partitions so that for the smaller half, all the values are smaller than the values in the larger half. Okay, well, even though it may not be a really 50% to 50% partition, but we want to guarantee that for one bucket, all the values are smaller than the values in the another bucket. Okay, and how do we do that? Well, our goal is we want to divide A from P to R, well, say P is the lower bound and R is the upper bound, to be two parts. So from P to Q, that is a lower bucket, and then we also have a higher bucket that is from Q plus 1 to R. Okay, and this is called partition. And if you bring in the idea of the recursion, and as you can imagine, after we have already done one part of the partition, and then for the lower half and the upper half, we can recursively do the partition. Okay, so we recursively do the partition until when? Until, well, there's only one value, and then there's no way we want to partition that even further, and then we can stop. And after that, actually this quick sort is done. So isn't that cool? Okay, so let's see the code. So for the quick sort, A will be a list. And then we have the P, which is the lower bound, we have the R, which is the upper bound, and as long as the P is smaller than R, so as long as the lower bound is still smaller than the upper bound, this means there are at least some value to partition. Okay, and then what do? We want to partition this list A, using the P as the lower bound, the R as the upper bound, and then eventually we are going to return the middle index as a Q. And after we have the middle index Q, we know on the left part, on the left side to the middle value of the Q, those are the values smaller than the value on the index Q. And on the right side, those are values greater than the value on the index of the Q. And then we have two parts. And then we just recursively do the quick sort on the left half and then on the right half. So that's a quick sort. And as you can see, this algorithm can't be that easy, right? So what's hidden? The hidden part will be the partition. So how do we want to do the partition? Okay, remember our goal. Our goal is that we want to have a middle value, and the middle value will be called the pivot. And on the left side of the pivot, those are values smaller than the pivot value, and on the right side, those are values higher than the pivot value. And then for the middle one, that is a pivot. And that pivot will be the index of that pivot will be the Q, and that Q will be returned from the partition. Okay, so this is our goal. We want to have two subarrays. And again, well, for the size of the subarrays, ideally, we want them to be 50% of all the values. But in reality, it can't be done. Well, if we have 20% on one side and 80% on the other side, we are fine with that as well. Okay, so how can we possibly do the partition? Okay, so my goal will be first, we want to have a pivot. Well, how do we pick the pivot value? And if I give you a unsorted list, and how do you pick the pivot? You don't know. You definitely want to pick the median if possible, so we can have a 50 to 50% partition. But we don't know what is the middle value or what is the median. So how about we just blindly pick one? So let's just pick the first value from the unsorted list and we pick that as a pivot. And if you're lucky, and then we are going to have a something close to 50 to 50% partition. And if you're unlucky, we may have 1% to 99%. So that's also possible. Okay, well, but anyhow, we just pick the very first value as a pivot. And after that, well, we are going to use two cursors. Well, we want to use the I cursor, and then we increase the I from the second of the index. So we move on and we move on. We want to use the I index to find a value which is greater or equal to the pivot. And then we want to use the J index from the very end of the unsorted list. And then we are moving it back. And our goal is we want to find a AJ which is smaller or equal to the pivot. So think about that. We are using the I index to find a value which is greater than the pivot. We are using the J value, the J index, to find a value greater than the pivot. And what are we doing there? So we want to move the smaller value to the left side. We also want to move the larger value to the right side. So when we are able to use the I and J to find two values, and this means we have already found a pair of the values and they are both on the wrong side. So what do? We want to swap them. So the smaller value we found with the J, we want to move that to the left side. And for the larger value we found with the index of I, we want to use that to the right side. So we just do a swap. And then we want to continue. So our goal is we want to use the I and J to visit the values. As long as we find a pair of the values, they are both on the wrong side, we want to do a swap. Okay, so this is the plan of the partition. And eventually we want to make sure that we return the middle index for the pivot. Okay, so let's see the implementation. And well, this is pseudocode. And by the way, I'm not really using the pseudocode from this textbook because that version is really weird. I want to show you another version which is more commonly used. Okay, so in this class, we are using this version of the partition instead of the one on our textbook. So let's see how it can be done. So we want to grab the A, and A, which is the list, and then P and R. P is the lower bound and R is the upper bound. And then we want to grab the AP, and then this X value will be the pivot, and then P plus 1 is the initial value for I, and then R, which is the upper bound, will be the initial value of the J. And then we want to just move those two cursors as well until we found two values on the wrong side. So we want to repeat the I minus 1 until we find a AJ which is smaller or equal to the pivot. And then we want to repeat the A plus 1 until we find a AI which is greater than pivot. So now we have a pair of those values. So hopefully I is still smaller than J, so we want to do a swap. So if I is smaller than J, we want to exchange those two values. And otherwise, well, what does that mean? So otherwise, if I and J are already on the wrong side, so I is already larger than J, and then there's no point to do the swap because those two values are already on the wrong, already at the right side. So we don't have to do the exchanges, but eventually, well, when those two cursors, they have already met and crossed, and we want to swap the AP, which is the pivot, with the AJ, and then we return the J value. Okay, so it might be hard to track this code if we just read this code line by line. So I want to show you an example. Okay, so let's do this one, and let me go back to my drawing pane. Okay, and we want to start, we want to have this value to be the x because this is the pivot. And then for the second value, that is the index I, and for the last value, it is the index j. Okay, and then we want to start this iteration, and we want to keep on reducing the j value until what? Until we find a j value which is smaller or equal to x. So the first value on the j index, that's fine because that is 7. 7 is greater than the pivot value, which is 5. So 7, you are on the right side, so I'm not touching the 7. So let me erase that. And how about the next one? So the next one will be 3. And for the 3, yes, this value is on the wrong side. So I'm expecting to move a larger value to this place. 3 is smaller than 5. So let's touch the I then. So for the I want to increase the I value until I find a I value which is greater or equal to the pivot. So 3, you are fine. So let me move the cursor down. Sorry, move the cursor up. So how about this value? 2 is also fine because 2 is smaller than 5. So let's move this up again. Okay, let's do 6. Okay, so how about 6? 6 is indeed greater than 5. Now we do have a pair of the values. So index I gives you a value greater than the pivot. Index j gives you a value smaller than the pivot. And I is indeed smaller than j. So what do? We want to do a swap, right? So the next part, we want to run this line of the code. That is, we want to swap the value of the AI and AJ, and then we want to move on doing the search. Okay, so let me just erase those two values, 6 and 7, and then I want to put 6 and 3. So 3 should go here, 6 go here. And after that, we want to move the I and j both to the middle. So, okay, I want to move the cursor down. So I will go here. And j will go here. Okay, and then let's continue the search. Okay, for the j, this j is 1. Oh, this is not cool because we have already found a j which is smaller than the pivot. So j will stop here. And how about I? So for the I, we are using the I to find a value greater than the pivot. So 4, that's okay, and 1 is okay. And then eventually I will be here because we are using the I to find another value greater than the pivot. Okay, so we have found another pair of the I and j. Those are the two values. AI is greater than the pivot and AJ is smaller than the pivot. My question is, are we going to do a swap? The answer is no, because if you check this condition, if I is smaller than j, we want to do the exchange. But in this case, I is already greater than j, so what do? We want to swap the AP with the AJ. So what are we swapping? So we are swapping this 5 with this 1. So let me do that. Okay. Oops. This is annoying. Okay. So now we can move the pivot 5 to the location of the j, and we are eventually returning this j. So when we are returning this j and the pivot value is 5, and what do we have? So on the left side, those are all the values smaller than 5, and on the right side, those are all the values greater than 5. And you are getting the index of 5, and this 5 will be used as a pivot. So eventually, we are able to get one part, which is the values all smaller than 5. I should say the value smaller or equal to 5. And then on the right side, we have another sublist, which are the values greater or equal to 5. And then, well, we don't have to touch the pivot anymore. This 5 will stay there. And then for the sublist on the left side, we want to do a recursive partition. For the sublist on the right side, we want to do a recursive partition. And then we want to do the recursive calls, and eventually we will have all the values sorted in place. Okay, so this is a quick illustration about the partition. Okay, let's come back. So what is the running time of the partition? So think about that. Well, there is a while loop, and you may find that if you have a for loop and then you know how many times we are visiting all the values. But if we have a while loop, how do we know when are we going to finish? So let me suggest you to think in another perspective. When we are doing this while loop, what are we doing? We are scanning through the values, and then eventually when I and j cross, it will stop, right? So how many values are we touching? We are touching slightly more than the n values, but anyhow, when this cross in, soon this iteration will stop. So anyhow, it doesn't matter we are touching the values with I or j, we are touching those values with either y or j, but we are touching all the values in the list, right? So do you feel this is a linear algorithm? Because we are touching only all the values once and only once. Okay? And then, well, let me ask another question. What's the best case of this algorithm? So for the best case, we are visiting them and then they are all sorted. Okay, so we like the fact that they are all sorted, right? So my question is, if they are all sorted, will that really be a good case? So you have to think about that. And then another question is, what's the worst case? Well, and if they are sorted in a reverse way, and is that the worst case? Okay, or if you assume that they are just random numbers, and that's already bad enough, and you can want to consider that as the worst case. So for this part, number one, you want to consider how many values we are touching, and number two, you also want to consider how the partition is done. If the partition is done with 50% on one side, 50% on the other side, and then you may feel we are doing less recursive calls, then we do 1% on one side and 99% on the other side. So this is also the factor you want to consider. Okay, so anyhow, this is not the code we have on our textbook, but this will be the version of the partition we are going to use in this class. And I highly recommend you to think about what will be the best case and the worst case of the partition and of the quicksort, and we will continue in the next class. So for this lecture, I ask you to read the full chapter 6 and plus the section 7.1. Okay, so this is the end of today's class, and then I will see you in the next class. We will continue our discussion about the quicksort. Bye.